welcome to Pseudorandom.
Hello, and yes, welcome to Pseudorandom. I am Colin Cunningham. With me is Matthew Borgatti.
Hi there. Hi, Colin.
Hi, how are you doing?
I'm actually doing really well.
Yeah, I could tell. It's making me feel a little better too.
All right.
I mean, not that I was doing bad in the first place, but you came by here today.
I came
to
with
talk,
purpose.
with purpose, a very interesting purpose.
Yeah.
Not by coincidence, to talk about an interest of yours, soft robotics.
I'm
Yeah.
the lead scientist at a company, Super Releaser, which
I've heard of it, yeah.
makes soft robots.
Make soft robots that, and you didn't just, you weren't looking for a gig. This interest sprang up in you. How? Like, how did this first spark?
So my background is industrial design. Went to school for industrial design at RISD. And then through it, I sort of discovered I really like doing conceptual design, but there's a hard edge to engineering where you actually have to solve a physical problem.
Right.
And it dictates a lot about what you have to do. And I went out, we did a lot of conceptual design at school, and I wanted to work on problems with teeth. And I got a gig inside of the special effects industry. Starting at, I did the Kyoto Brothers, ADI, Animal Makers, the Character Shop. And we did a lot of mold making, casting, machining, a lot of things where I was working with roboticists.
Maybe some actual teeth.
Actual teeth. Yeah. I was on Snakes on a Plane casting real dead snakes. I was on Team America World Police, sewing itty bitty costumes. And what I learned in there was there's actually a place to get a lot of motion and get a lot of life and work out of soft materials as much as hard materials, because in the effects industry, you're using material properties together in a way that you seldom see in other fields of robotics. And so I sort of stewed on this for a couple of years and then realized my background in 3D printing, my interest in CNC machining, because I had been a machinist in special effects.
They could all converge.
It bubbled up into this thing where I realized there could be a way to make some really cool new mechanisms if you made a really consistent method for iterating, where you could print a mold, cast a thing, test it out, and then go back to the start, just printing and casting, so you could do all these experiments real quick.
And this was, you're thinking with soft materials in particular, with inflatable materials in particular, and this was, because you're saying special effects, and I'm thinking you want to. The first thing I think of when I'm relating to what I know of your work here is you want to make something breathe, like it's alive, like something pulsate, something inflate and then deflate and that's super interesting that it was special effects. That makes total sense now. You're saying, there's a bridge. There's
this there's a thread that sort of runs through the design of biological organisms that is, when we see it in the world, when we see something that looks like life, it's got these relationships, these kinematic relationships. When you see a robot smile and the wrinkles don't work it's because the materials aren't interacting in the way that we think life should.
It's not all moving as one.
But there are other
specific motions programmed in there.
And there are other motions that are actually useful motions that you can get real work out of. Think of a heart, and you have these heart valves that the heart squeezes, and it's composed of these 4 chambers that all have check valves on them. And the whole thing is soft and squishy, but it turns into this sort of reciprocating motion. It's this motor.
And they all work together in a way they respond to.
Yes. And it's all
one closes another.
And it's all soft, and so when your chest gets compressed because you're leaning over, or you have somebody standing on you or something, your heart still works.
Right.
And it's sort of what I started thinking of is if you could create a design vocabulary for creating soft robots, then you could start solving all of these weird problems.
And that's the thing, you say create because there wasn't one. There wasn't a vocabulary. There wasn't an established area like this. You're pioneering here. 5 years ago when I started out, it was all just sort of a fancy of mine. I was lucky enough, Jim Brett, who was one of the founders of Z Corp, has a lab where he experiments with powder printing, and it doesn't matter too much to him what goes in his printers. And so he offered me some free time. As long as I helped him out and helped him clean up the lab or run experiments, he'd give me unlimited time on printers. And so I threw just a lot of designs at the board. You're gonna need it.
Yeah.
Unlimited time.
And so I just printed and printed, and at that time, FDM printers weren't quite in a state where they could reliably create a watertight mold. And so this was the best way for me to dive through creating these watertight molds for casting silicones in and stuff like that, and starting to work out a vocabulary of methods and processes and good materials for soft robots. I'm not the first one to ever do this. There's like the Whitesides lab and the Weiss lab, and other lab has a thing called Nubotics.
Still imagine it could feel like you were definitely the first one doing it when you have so little to build upon, so much new. Instead of looking at the negative, so many new things you're discovering that aren't really documented or established.
And if you're a car designer, you're like a group of car designers, and you're like, we want to make this, Shelby-inspired supercar.
We stand on the shoulders of the ones before us.
And so you could ask to you could interview a bunch of classic car enthusiasts and get a repertoire of awesome mechanisms, and call up mechanical engineers to be like, if you wanted to manufacture this, what scales well? And they'll be like, oh, these magnesium castings. I can't do that.
Can't do that. It's all you.
What's the best soft robot on the market right now?
Yeah. What sucked when I did it the last time? I want to avoid this time. Yeah. So I mean, we're talking about these in the abstract. Of course, you've brought along some evidence.
Oh yeah.
Of your work.
I've got some squishy robots.
This right here. This a little unassuming, cute little guy. I know people must personify and say cute and stuff. Right? Can I handle this?
Yeah, feel free to squish it and stretch it. Part of the point of that one, it's called the Glaucus, named after the blue sea slug, the Glaucus atlanticus.
Glaucus, it even has a cute name. I mean, it's a personality.
Yeah. So the point of this project.
Really cool.
Yeah, it's Smooth-On's EcoFlex 0050, which is just a really super soft, thin silicone, so that when you pour it, it doesn't trap bubbles that easily.
I could feel chambers inside.
Yes,
of
it has an interior structure of ribs. Yes,
right.
It's essentially made. It's an outer shell of a mold, I put waxes inside, and so when I cast the silicone between the shell and the waxes, you get this specific structure of it that when the waxes melt out, you have all these internal chambers. It's like plumbing. And so you have this left-hand wax and this right-hand wax that are near each other but don't touch each other. And that gives you what happens on the left hand and on the right hand when it inflates, is you'll have this one circuit of wax, one circuit of piping that inflates, and the other circuit of piping, and that gives you its walking motion.
Right, the inverse of the chambers of the wax.
Yeah, I can hook it up.
Oh yes, please.
If you want to see.
Yes.
Yeah, so the way that this dude works, and this is sort of very experimental, and I'm always poking at it and playing with it. But this is to sort of demonstrate a method and a concept for iterating on complicated robots, where like this,
Do you want to put him down on the ground for the other?
Yeah.
We have this other camera down here.
Yeah, there we are.
Yeah, there. Perfect.
Right. So this one, like when you inflate the left-hand side, you get that left arm going, right-hand side, right arm going, or it's actually not left and right arm. It's sort of each side of a freestyle swimming stroke.
Okay.
So you have one motion, and then you have its mirror on the other side, and putting the two together gets you locomotion. Although this one, I think this one has seen better days.
Right. He's it's for handheld stretching and and demonstrative fun.
One of the eternal bugbears of soft robotics is tiny differences in how things are made and cast can have a huge effect on the final properties, the final dynamics of the system. And so every Glaucus is a little bit different. This is my latest design and my latest casting.
But we have more examples of. Yeah. Do you want to talk about that first design that you had on the we have an image of the claw, the gripper?
Oh, the gripper. Yes. Let's talk about the gripper.
Because that's probably the first thing I think of when I hear soft robotics is.
Yeah, grippers and manipulators.
A single arm. I mean, the Glaucus is very cool, but it's seems really advanced. This is what I think of is. Well, you see here, like the separate fingers and those chambers. That's really straightforward, like that.
Yeah.
I mean, from just to ingest as a concept.
Yeah, I actually made this. So instead of the Glaucus is sort of a demonstration of a system for manufacturing robots. I made this dude as more of a way to get people playing with their own soft robots.
Inspired by crinkle fries, no doubt.
A little bit inspired by crinkle fries.
It's okay, it's not really inspired by crinkle fries.
The Weiss lab and the Whitesides lab have done a lot of work on digits. They have a thing called a NewNet actuator, which is part of their soft robotics toolkit, which is very effective, which also uses ribs to do its actuation. Essentially, whenever you have a rib, you're controlling the direction of actuation, because the stretch will happen perpendicular to the rib. You know, sort of like, you know, electric fields and magnetic fields will happen perpendicular to one another. Actuation, stretching will happen perpendicular to supports. And so if you want something to bend in this way, you put supports in this way.
Supports being more material, basically.
Yeah. And so you can start to control the direction of bend. And so this is sort of inspired by the Soft Robotics Incorporated gripper. But I've been trying a whole bunch of geometries to figure out what grips best and what's something that's really simple and straightforward that people can use as an avenue to make their own soft robot. And so for like this dude, the molding is all on the floor. Sorry. The molding is actually really simple and straightforward.
Okay, can we show that in the overhead?
Yeah,
that's cool. So that's the molding for one of the fingers.
One of the fingers. Each one of the fingers. These print without support material. I'm very interested in geometries that don't take a lot of technical wrangling to duplicate yourself, where the number of steps is really straightforward, really easy to instructabilize. And so this dude prints in one go. All of the components print in one go. They require no support material. And the way this mold goes together is you just snap the core in with the mold shells and then put them together with a rubber band and cast it. And then that gives you each of these fingers.
Okay, so that they are cast as a single piece. These aren't, because I'm seeing this, I'm thinking like it's adhesive or something. And you could show that in the overhead too. Actually,
this one, this one is a little bit, it has a little bit of a twist on it, where I've actually been experimenting with incorporating cloth in with the mold. There are all sorts of interesting things you can do by combining materials.
That won't stretch the same rate.
And so we've been doing all sorts of experiments with combining different materials together to get different properties, having some reinforcing, some stretching even more. I've created casting processes where we can layer different silicones on each other, so you can gradient from a very hard thing to a very soft thing.
Wow, seems like a lot of fun.
It's really exciting, you know.
I mean, it's hard but fun.
It's really rewarding. I wish there were more ways to create a community of people all playing with this. I've got a soft robotics forum.
Knowledge,
where so you every so often have XYZ Aiden Leitch on here with his own soft robots on the Yes, and so Aiden's always creating new stuff, and he has actually he's our intern this summer at Super Releaser.
Oh, nice.
And so he's been really good at experimenting, with just tons and tons of different designs and putting them on the forum and stuff, and that's been super rewarding.
I lost my train of thought when I was going there.
No
but
worries.
You must. You develop because you don't have a lot of tools established, of course, like we said. I mean, this must be just developing instincts with design. I would think I would just be building. I wouldn't even necessarily be able to explain it out loud to somebody. Like, well, I'll throw another. Look, I'll just show you.
Yes.
You know.
Yeah,
I could talk about the basic ideas, how the fabric would change the behavior, but I would just I would move it into feel like more of an instinctive art.
And I'm always learning about it too. Like I'm always learning. Like I designed this with sort of, you can see it's kind of thin or at the base, and so sort of unconsciously, what I did was I also created a weak point where it flexes more. And so there are all these things that you have to take into account when you have these nonlinear systems, where some of it's actually going to stiffen due to the inflation, and that process is actually going to load force somewhere else. And it's the kind of thing where we don't have simulation tools quite yet.
That's really, I guess, what I was,
the
way I get at what I was thinking is, there isn't a simulation. This is in your head, you're simulating.
Yeah, and my solution for it is, I've been doing this a long time and I still don't get it right the first shot. This, I have a previous design here that is just barely functional.
Oh, wow. This is sweet.
Sure,
Show that
let me
detail on the overhead too.
Put that under here.
Much different approach, right?
Yeah, so it's a very different approach. This one is entirely ribbed on the inside, so it moves a lot like the Glaucus.
Okay.
And what I found with these guys is that they really, really want to flex in one place. With this design being tapered, essentially as the interior area, the cross-sectional area gets smaller up towards the tip, it doesn't want to flex at all.
Right.
And so
maybe revisions, you would make it thinner at the top to try to encourage that, but
or
obviously
use a higher durometer silicone, where the silicone is going to even it out.
All right.
There's like a capacitive effect of mass of silicone, or of durometer of silicone. So if each element...
Durometer.
Yeah.
Definition.
It's really just a fancy way of saying softness.
Okay.
And so higher durometer, less softness. So there are multiple scales. For some reason, engineers didn't want to make it easy on you.
Oh, no. We got to, keep out the newbies.
Got to keep out the hoi polloi. Mm-hmm. And so there are multiple scales, but all that it really takes to know is that the lower the number, the softer the material. So on the Shore A scale, which is sort of a middle of the road, there's O and then A, and I think there's B. On the Shore A, the very, very lowest is like putty. It does not resist your touch, super duper soft. As you get higher, like a Shore A40 is about the durometer, the softness of your skin. And then Shore A100, as you get higher up the scale, you're talking about like the plastic in a hard hat.
Right. I will try to start applying this durometer to perhaps pasta.
Yeah. Yes.
That'll be my first use.
And it's actually sort of a useful way to think about stuff, because like how you give up, like imagine on a piece of steel like a sword. Mm-hmm. You want hardness, but you also want durability. Mm-hmm. And they're materially linked properties. Where you want something that's a lot more durable, you might have to give up some hardness, because if the blade's made of glass, you can just snap it over your knee.
Brittle.
And a soft piece of metal that does very well with bending might not take as well of an edge. Mm-hmm. And so there's that same balance with the durometer of silicones. Higher durometer silicones have different dynamics when they stretch, and they often have a higher tensile strength. And so you can stretch them a lot harder before they tear. Like a very soft thing, often it's easier to tear.
Mm-hmm. Sure, and this is all being loaded in, and when you're thinking about something instinctually and designing instinctually, I would think.
Yeah.
You brought in a lot of other great visual examples.
Oh, sure.
What was the next one you had?
So I have
more
some
pictures of Glaucus. I know. Oh, we've in a video of Glaucus actually.
Yeah, let's
moving. Right?
Let's take a look at it walking. So, do you want to talk about the difference between soft and hard robots?
Of course I do. No, I mean, that's, elemental here. You're in a different world. Robots are metal and shiny.
Yeah.
Clank.
Well,
clonk. Click.
Yes. So if you look at the history of all actuators, all moving things that have ever existed, you start with early biological life that has all of these weird little stretchy things inside of it, like the ATP molecule itself, that is like the fundamental motor of so much animal life, is a little stretchy thing. It's a little spring that does work. And what that ends up with systems that are like floppy and dynamic, and they are sort of changing how tense they are. They're like giving little bursts of tension where you're changing something from floppy to stiff and from long to short. Like that's the way most muscles work, and that's the way sort of the ATP molecule will pull down on like a chain of proteins.
And as it builds up into this big system with all these complex behaviors, really.
Yeah, and so even a hard-shelled organism like a crab is going to have soft insides which are actuating it. Like a spider has a hydraulic distributor inside of it that's pushing hydraulic energy to its legs. And then you have human beings creating mechanisms, and we've done this in a very different genre, in a very different way. And one of the advantages is we've made very powerful mechanisms. Like the amount of caloric energy that like a car puts out is huge. We're able to like harness a lot of mechanical energy to do work. But one of the disadvantages is things that biology has conquered really well. It's done through being able to balance on these weird environments or these weird situations where in traditional robotics, what's difficult is, not being able to take a fall and then just sort of like slump into it and then correct yourself.
Being squishy is adaptive.
Yes.
Yeah. Makes sense.
Yeah, and I'm not a purist where it's like there may only be soft in a soft robot. I'm excited at the idea of like how far can you go with all soft, but it's really I wanna go hard into what soft materials can do to explore how you integrate them into better robots.
I mean, it makes sense that we do things the hard way, not the conventional sense of that phrase, because it's easier to calculate, I would think. It's easier to simulate.
Yes.
I've heard a lot about how difficult it is to simulate the behavior of rivers.
Yes.
And so in the end, a lot of the researchers and scientists around it just say like, look, just build a small river, just simulate it with water, just because it's easier, because this math it's still a little too hard for us. And I could see, it must be similar parallel here going on, some difficult challenges. I guess that's why I'm thinking of instinct in the design.
Yes.
And I like the element.
My solution is iteration. Like you have these are nonlinear systems where as soon as you add like an elastic element into the system, unless it's like a car tire, something that's very even and super known, small changes in one place have a large effect in another place. And there are so many systems that work like this, like a Lorenzo tractor is a great example, or a 3-body star system, where you can calculate a 2-body star system to the nth dimension. Like you can do it forever, but add an element in, and suddenly it's completely nonlinear. And there are so many things in nature, in life, and in science that are like this. And they are difficult and ambiguous problems to solve. And sometimes we shy away from them because the ambiguity is very hard to certify, to wrap our brains around, to guarantee that it's going to be the exact same and you deliver it every time. I mean, I wouldn't want to live in a building where people are like, I don't know if it's going to fall down.
Yeah, it looks pretty good. It hasn't fallen down yet.
Yeah, but on the other side of that, I think there, especially as we learn to use 3D printing and materials science and this like really interesting cohabitation, there are all these avenues to take advantage of nonlinearity and to prototype and experiment our way through it.
It's a little scary for some people at first.
Yeah.
It's first stepping out. It's going to take some time and iteration, like you said. I
mean, NASA for the longest time really, really wanted there to be a hard spacesuit. They wanted a hard, like mechatronic spacesuit.
Space crab. Yep.
Yeah. I think it was called the Puma system. But there were a bunch of really beautiful.
I've seen it referenced in sci-fi, maybe with like the circular
with the circular,
joints.
Yes.
Kind of looks
Fashioning
like
Apollo.
A big gorilla pod, like
Fashioning Apollo is a wonderful book on it. The history of the Playtex Corporation and its relationship with NASA, International Latex, which makes bras, designed these spacesuits for the first space missions because they were the people that understood all the things that had to go together. And lots of people tried to make a hard mechanical spacesuit, and it turns out that the body is in itself so complex that you can't make enough mechanisms to make a good hard spacesuit. Like all the room that you need between the mechanisms and how like how would you possibly have a bunch of things that like are these bearings that fit over these perfectly machined surfaces?
It's a little bit hard for me to watch Iron Man in the movies.
Yes.
Because it's a little, it breaks the suspension of disbelief so much for me because I'm like, oh, come on. I could get a lot of other things, but
like, it's a super powerful armor that can resist explosions that's light enough to carry around in a suitcase.
That's so comfortable, apparently. That's really what I'm thinking.
Doesn't
like,
pinch in the crotch. Where does his pants go?
Yep. Yeah. I can get with, it controls itself, and even vision, moves through walls or something. But this we forget how complex we are.
Yes.
Basically. Yeah.
And that sort of like.
We have the walkie video too.
Oh, excellent! Yes.
Speaking
of complex moving things,
we have the walkie video.
Wait, which one is this? That was inspiring.
Thank you.
Made it all the way across.
Yeah.
I was about to say he, but they're not gender specific.
No, they're gender neutral robots.
Yes, good. So that was somewhat transparent Glaucus.
Yeah.
You could see the chambers.
Yes. So
within, unlike the other one.
Yeah, that's cast out of an untinted. I like tinting silicones because I love blue as a color.
They're cool.
But that was an untinted silicone. That was a Glaucus at Smooth-On's headquarters. So Smooth-On actually did the people who manufacture the silicones that I use actually did a little thing on like this person is using a Glaucus and they powered it with an air control system that they have inside of their shop, and they got even better performance than I was able to out of mine. And I'm always like a little bit like, oh man, you got
yeah. Maybe I could. Yeah.
If I could only have my thing do that well, it's sort of like someone else's, your dog listening to someone else way more than they listen to you.
Right. Wow, I didn't think of it that way. Yeah. Oh, yeah. But I'm so into this. Why do you have the? Yeah. Okay. No, I got you.
Yeah.
Right. It took me a moment.
Yeah, and so it was cast out of just a regular old silicone that you can buy on Amazon. I think we have a picture of me casting over here. So that's a Glaucus mold with a wax inside of it, and so I'm cleaning up the first casting in the silicone. So the way that I embed the wax in a known place in the mold is to actually take advantage of the chemistry of the silicone.
Oh, really?
So what the silicone's going to do is it starts out as a bunch of little molecules that want to chain together. And as they chain together, the silicone's durometer is going to go up. And there's a stage at which it's a gel. So it's stable in its geometry, but it still has lots of open bonding sites for more silicone to knit into these long chains and be super strong. And so it'll be dimensionally stable if you treat it right. So what I do is I have a support for the wax, put the wax in the support, put the mold around it and pour silicone in, and that holds the wax in place. I can take the supports off.
Yeah.
It's like scaffolding. I can take the supports off, put the new mold on, and if I do it at the right timing, the two silicones will be undifferentiatable.
That sounds specific, intricate. you just get the hang of that, and it's good. It's reliable. Wow.
What you really need to know is the silicone that you're using. If you're using anything to accelerate or retard the cure, technical word, then you have to take into account the chemistry and the heat of the day, because all catalyzation reactions are going to happen.
Ideally, you want a temperature-controlled lab?
Yes, I have an air-conditioned lab, but for every 10 degrees C, you double the rate of catalytic reactions.
Wow.
And so you need to take that into account when timing out the thing, but I've gotten it down to like, well, it's going to be 20 minutes. And so we wait 20 minutes, set a timer, and then I also have a little cup of silicone from that same casting to touch with my finger because it gets less tacky over time. And so while it's still tacky but dimensionally stable.
With resins myself.
Yeah.
You keep your sample on hand.
Yeah.
And so were there any more example images from your casting here?
Next,
you haven't been working alone on this, right?
No, for a lot of the Glaucus and a lot of the early work, it was just sort of me as a hobby.
Right.
And as I formed Super Releaser, my company, this is Kari Love, my business partner at Super Releaser, and this is her cleaning up a wax that goes inside of the Glaucus. And what's been interesting is that my experience is sort of this CAD mold making, casting, 3D printing. Her background is actually spacesuit design. And so
specifically spacesuit design.
She is a Broadway costumer and a spacesuit designer. And so Kari has actually worked for Final Frontier Design, developing their spacesuits. And a lot of the focus in her work has been figuring out how to make sort of one-size-fits-all spacesuits, because commercial spaceflight is going to rely on cutting the costs of traditional spaceflight. So, depending upon what the mission architecture is, maybe you don't need a spacesuit that's the most dexterous as possible or custom tailored. Maybe you can have a spacesuit with straps on it that many people of different heights can wear safely.
Sure. Ideal.
And so that's been a lot of their research and creating tester suits. And what she has taken away from a lot of this is that, Broadway costumes, they have to deal with a whole lot of abuse and stay looking and acting good. And they have to interface in a very complex way with the body. Like if you're wearing a headdress that is like also resting on your shoulders, it can't look super unnatural when you move your shoulders, but it's got to take the weight off a dancer.
Is very involved, yeah.
Yeah.
It has to be conducive.
And then there's this knowledge of technical fabrics in both costuming and in spacesuits, where you have to know the dynamics of the fabric and have ways to sort of estimate what you need in a situation and then buy it, test it, validate it.
Again, she builds up a lot of design instincts too, I'd imagine. You guys must have a lot of overlap where you meet here, obviously, because you're working together on this.
Yeah, and so I've been teaching her through what I know about casting, and she's been teaching what she knows about the material science and the way you apply these soft systems together, the way you like get cloths together to get a specific dynamic out of the join between here's a soft, here's something that's kind of stiff, kind of stretchy, kind of soft. When they come together, what happens?
Right, and you have I saw this before when we were prepping. So why gloves first?
Yeah.
And you mentioned because it has an example of every circumstance, every physical circumstance that's necessary on a full-size suit.
Yeah. So
and it's funny when you think of your hand. Yeah, it does have so many little complex motions and relationships in there, right?
Yeah. So this is a slide from a talk Kari gave to a NASA educational group recently. There's a STEM education initiative inside of NASA to try and get teachers teaching with material NASA has put together over the years on like how do you explain space to children? How do you close the loop on here's what engineers do? How do you get children excited about what that actually is? You could solve space flight problems. That's why you should pay attention in calculus.
Yeah. It's application.
Yeah,
Don't forget.
You're going to know when a train arrives. You might be able to help get the next Mars lander up.
Right.
And so that slide is about like the hand is sort of has an example of every mechanism that you would need in an overall body space. So there are areas where it goes in. There are areas where things come together really tightly. There are areas where the suit has to touch an exact spot on the body to fit right, like at the fingertips.
And to break it down into perhaps a more simple relationship, but on a larger level.
Yeah.
The elbow. What is this called?
So this is called the new cuff, which is a exoskeleton project that we've been working on. Just one point before we leave spacesuit gloves, we actually just finished a NASA contract developing a new kind of spacesuit glove.
Oh.
Yeah.
That's pretty incredible.
Yeah, it was
with NASA, the one I know.
Yeah, not NASA, NASA.
Right,
Yeah.
cool. That's awesome.
Yeah, so we just submitted all the deliverables. Final Frontier Design was the prime contractor, and we specifically did soft robotic elements for it. We did a wrist gasket that there are two systems in the suit. This mechanical counterpressure one, it's essentially cloth pulling in on your hand the same amount of space is pulling out, and so the pressure evens, and you're just wearing this layer of cloth in space, and it's super dexterous, and it's very easy to move your hands around. You can sort of touch all your fingertips together. And the idea, in contrast to a big inflated, Michelin Man glove, is how much mobility you would have to do intimate repairs in space.
I could imagine not much.
And so that sort of one way that it comes in is that we've actually been putting our money where our mouths are when it comes to applying these things to real problems that you could not do with a traditional robotic sensibility.
Sure,
Yeah.
that must feel really cool.
Yes,
having a pressure
wearing a pressure
glove.
garment,
yeah, or a pressure garment in general.
Yeah, it's super. It's
I've
super
never
cool.
even been inside of an inflated costume, but I should try it sometime. Maybe I'll ask you to borrow one. You probably have a really cool one. So you mentioned briefly.
Yeah.
We have one here.
Yeah. So this is the new cuff. So the idea behind it is
My old cuff was not nearly as cool.
It's new like pneumatic. The new cuff is a concept in exoskeletons. So I feel that manufacturing makes a huge difference to the availability of assistive technologies. So
It makes them available.
I became aware of this problem in cerebral palsy orthotics, where children grow relatively quickly, like their bodies change dimensions fast. If you have a disease that you need assistive technology to be custom made for you, like say you have a thing that tries to adjust your foot to be in line. You want to try it on?
Yeah.
So say you have something to try and adjust club foot. What will end up happening, and so the point of your elbow just goes right here, and it can go over the shirt. It'll have to be modified many times as you grow, and that can get very, very expensive. And so what we're experimenting with is applying soft robotics technologies to one-size-fits-all adjustable exoskeletons, where the force and the power that you need to do work, like for someone with cerebral palsy who's latched into a clenched position, you can actually give them some power to replace the power of their tricep and get their arms back out and working. But we want to do this in this sense.
This is my microphone. I set up right there.
Okay.
Thank you, Phil.
We want to do this in the sense where it's going to be affordable and repeatable and safe. And so if you pull your arm in, as if you've sort of got a clench.
Okay.
The idea is to get your arm back out. And so this, I might switch this out for the other air supply.
It's a strange sensation.
So I can give you the full power here. I can give you all the beans.
Well, that was like an assistive nudge. I can feel definitely.
So let's take you up to the full 20 psi. To give
Let's do it. I'm ready, Matt.
Cut me.
I'm gonna clench. I'm gonna fight it.
Yeah. So it's an interesting sensation, especially that it's not quite like a motor. It's not simply adding torque to your arm. It's an interesting system.
Huh. Wow. Incredibly rigid. Wow.
Yeah. And so the idea is that
it's hard. I don't know if I'm going to damage anything by trying to fight it. But
you can't really damage it. I mean, if you stabbed it, I suppose.
Yeah,
this is actually a Kevlar reinforced plastic.
Yeah, the pressure is all being distributed among the bladder, if you will.
Yeah.
Wow. Yeah, I could see that being a pretty amazing thing to someone who's lost mobility in their arm to be able to.
Yeah, and they're inexpensive to produce. It's not made of a lot of complex things.
Right.
We're
it's
trying to learn
intrusive.
more.
I mean, it's comfy.
Yeah, it's always hard where like the cross-sectional area of the bar has a large influence over how much power it has. So figuring out how to maybe distribute that to a lot of smaller bars so it doesn't stick out so much. So you could even wear it under clothing.
Sure. Yeah, I could totally see that working under clothing as is.
Yeah.
I mean, I wear some baggy shirts.
Yeah, but like these are the kinds of concepts that we feel emerge out of soft robotics, where this is fairly inexpensive to manufacture, or we believe it would be if we could take it all the way through.
Right.
We've super Laser just graduated from this program that the NYC EDC puts on called eLab, which tries to get New York companies staying in New York to do medical technologies, and we've learned a ton about actually how much work and money it takes to get through certifying a medical device and getting it all the way home.
Massive, no doubt.
Yeah. But what we're trying to do is take these concepts and work with people who are already in the space of like trying to create orthotic and assistive devices, larger companies that already have this chain going where they know how to take things through the FDA and essentially make a pitch for like, think soft robotics. There are these actuators and mechanisms and systems where you could actually make this huge help to people.
That's awesome.
Making an inexpensive universal device.
Jump in with them already on the mission instead of like competing separately or something. It would just waste time, and people would go without the benefits of this innovative.
And what's hard as a small company is we only have so many resources to put around. And what we're really excited about is playing with a lot of technologies and having our fingers in a lot of designs that shape the future. So like right now at Case Western, there's a student, Momotaz Begum, who is she's a biomechanical engineer, if I remember it right. She's working on an AI system where we made a knee version of this cuff that's specifically for patients who have an asymmetrical gait because they've had a stroke. The idea is you could have this one-size-fits-all robot, to get the gait even and have an AI train the knee cuff to when to actuate, differentiating it for each patient, because with each patient, their walk and their stroke are both going to make them a little bit
tailoring over time for the user.
Yes. And so I really like that idea of partnering adaptive technologies with this soft compliance.
That seems really, really important, especially when you're taking to a metallurgical level here. It's about adapting, it's about being adaptive. You think perhaps some of the instincts of the physicalities that you've picked up are being applied on larger levels to, strategy using this technology.
Yes, like what's on video right now is we have this concept for interfaces between residual limbs and prosthetics. People are highly individuated when it comes to an amputation. And what we want to do is figure out if there are ways that we can get a better interface between a standard prosthetic and a person's unique individual amputation.
Right, yeah, there's a lot of pains.
Yeah, because distributing the force.
Direct interface.
Yeah, because if you have, say you get an above the knee amputation, you don't want to load all of the force onto the femoral end. Because the skin can't take it over time. You need to distribute that force up all over the leg.
And again, just like I was saying with the cuff, I can't break it because the pressure is distributed. You're distributing it very evenly.
And
this is I finished your sentence.
Oh no, it just what's very interesting is the opportunity to use these soft dynamic properties to choose where the force goes, where there are areas where you could put air in the silicone to make it spongy and absorb impact, but there are also, silicone acts a lot like water in the fact that it doesn't actually compress at all. It's incompressible. And so you could also use that to put force places. And so we're even using that to transmit force in the case of, we have these little actuators for a system for diabetes therapy that actuates the foot. And because the silicone can't be compressed, we can actually put a little force over here and get it transmitted over there,
I think,
like hydraulically.
I think that you're distributing and filling all the spots on this metallurgical level, and finding where it fits, and improving a lot of things.
Doing our best.
This is honestly a lot more we had to talk about than I realized we would. I'm like, wow, this seems really deep and really cool. This is gonna be fun. I could talk to Matt about this.
Thank you.
It's about 3 times as deep and cool as I expected.
All right,
Is it?
Times
Were
is a good
you
number
going
of
for
times.
4? I'm sorry.
3 times.
Next time.
Yeah, I just.
We'll talk again. Thanks for coming on and talking.
Thank you so much.
That was completely awesome.
Lovely. Thank you.
Thank you, man. Thank you, everyone.
Bye.
For watching.